Chapter 5.2, Multiplying and Dividing Radicals. When multiplying radicals, we multiply the coefficients with the coefficients and the radicands with the radicands. The index of the radicals must be the same in order to multiply or divide them. Example, multiply using the distributive property, simplify where possible. 5 square root 3 times the square root of 6. Multiply the coefficients times the coefficients. For a square root that doesn't have a coefficient, it just means it's 1. 5 times 1 is 5. And then square root, they're both square roots, so we can multiply them. 3 times 6 is 18. We have 5 times the square root of 18. We want to simplify this. Let's make a list of our perfect squares. 2 squared is 4, 3 squared 9, 4 squared 16, 5 squared 25, 6 squared 36, 7 squared 49, 8 squared 64, 9 squared 81, 10 squared 100, 11 squared 121, 12 squared 144, and so on. I want the biggest perfect square that divides 18. Half of 18 is 9, so it can be no bigger than 9. And I see that 9 is a perfect square, so that's going to be my number. I get 5 times the square root of 9 times 2. I can evaluate the square root of 9 to get 5 times 3 square root 2. And 5 times 3 is 15. 15 square root 2 is our simplified answer. Negative 2 square root 11c times 4 square root 2c cubed minus 3 square root 3. So you want to take this whole thing and multiply it into the brackets. So to each term, and it states a restriction for us, c has to be greater than or equal to 0. First term, coefficient times coefficient. Negative 2 times 4 is negative 8. They're both square roots, so we can multiply those. 11 times 2 is 22. C times c to the 3 is c to the 4. Second term, negative 2 times negative 3 is positive 6. Square root, 11 times 3 is 33, and then we have c. We want to simplify these. What's the biggest perfect square that divides 22? Half of 22 is 11, so it can't be any bigger than that. So we're looking at 9 and 4 for our options. 22 divided by 9 is a decimal, and 22 divided by 4 is a decimal. So that just means we cannot simplify this any further. We can simplify the square root of c to the 4. Negative 8 square root of c to the 4 is c to the 2. We're dividing the exponent by the index. So 4 divided by 2 is 2. Square root 22. Plus, we have 33 under the square root. Can we simplify that? Half of 33 is what? 15, 16 and a half. So we're looking at numbers smaller than 16 and a half. Does 33, can 33 be divided by 16? Don't think so. 33 divide 16. We get a decimal. 33 divide 9 doesn't work. We get a decimal. 33 divide 4 doesn't work. We get a decimal. So again, that just means that the square root of 33 can't be simplified. So we are left with 6 square root 33c. And then we can't add these two. These are not like terms because this one has a c squared in the coefficient. This one does not have a c squared in the coefficient. This one has a c under the root. This one does not have a c under the root. So they are not like terms and cannot be added. Then this is our final answer. For square root 2 plus 3, all times root 7 minus 5 root 14. Just like any binomial multiplication, we multiply the first term times each of those, and the second term times each of those. 4 root 2 times root 7 equals 4 times the root 14. 4 times negative 5 is negative 20. And then root 2 times root 14 is root 28. 3 times square root 7 is 3 square root 7. And 3 times negative 5 square root 14. 3 times negative 5 is negative 15 square root 14. We want to simplify. Half of 14 is 7, so our only perfect square that we can even consider is 4, and 14 is not divisible by 4. So we can't simplify square root 14. 4 square root 14 is as simplified as it gets. Minus 20. 28. Half of 28 is 14. So in our list of perfect squares, we can look at 4 and 9. (28) divided by 9 is going to give us a decimal, but 28 divided by 4, we get 7. So we can write this as 4 times 7 under the root, plus 3. 7 is a prime number, so it's not going to be able to be simplified, and then minus 15 square root 14, we already said can't be simplified. So we can square root the 4, and we get 4 square root 14 minus 20 times 2 square root 7 plus 3 square root 7 minus 15 square root 14. Then we can combine our like terms. I have root 14, and then I have root 7, root 7. 4 root 14 minus 15 root 14 is negative 11 root 14. And then I have negative 20 times 2 is negative 40 root 7 plus 3. So negative 40 plus 3 is negative 37 root 7. There's our simplified answer. Dividing radicals. Divide or reduce coefficients with coefficients and radicans with radicans. Again, the index of the radicals must be the same in order to multiply or divide. Step 2, for dividing radicals, we need to rationalize the denominator, which means we need to make it so we don't have any roots in our denominator. For a monomial denominator, if the denominator is a monomial square root, multiply the top and bottom by the radical in the denominator to rationalize the denominator. If the denominator is a monomial cube root, multiply the top and bottom by the radical twice. First example, 10 square root 6 over 5 square root 10. Step 1, we want to reduce. Our coefficients, 10 and 5, we can divide both of those by 2. We get 2 and 1. Our roots, 6 and 10, we can divide both of those by 2, so we get 3 and 5. We don't really need to write this one coefficient, we could get rid of that. So 2 square root 3 over square root 5. Now we're on to step 2, we need to rationalize the denominator. We have a square root on the bottom of our fraction. We want to multiply top and bottom by that square root again. So 2 square root 3 over square root 5 times square root 5 times square root 5. This becomes 2 times the square root of 3 times 5 is 15 over square root of 5 times 5 is 5 squared. Now, what is the square root of 5 squared? Well, square root and square are opposite operations, so they undo each other, and we're left with 2 times the square root of 15 over square root of 5 squared is just the number 5. We no longer have a square root. This is our simplified expression. Next one, 3 cube root 10 over 12 cube root 6. Step 1, reduce. Coefficients of 3 and 12, we can divide each of them by 3. We get 1 over 4. Cube root of 10 and cube root of 6, we can divide both of those by 2. We get cube root of 5 and cube root of 3. We don't really need this 1 coefficient on the top anymore. We can get rid of that. Step number 2 is to rationalize the denominator. This is a cube root, so we have to multiply the top and bottom by the cube root that's on the bottom 2 times. We have cube root of 5 over 4 times the cube root of 3. We want to multiply top and bottom times the cube root of 3 times the cube root of 3. And on the top as well, times the cube root of 3 times the cube root of 3. We get on the top the cube root of 5 times 3 is 45 over 4 times the cube root of 3 to the power of 3, because we have 3 times 3 times 3, that's 3 to the power of 3. And then cube root and cubing. Those are opposite operations, so they undo each other. So we're left with the cube root of 45 on the top over 4 times 3, which is the cube root of 45 over 12. And we should actually check that our radicals in the end can't be simplified. Let's make a list of perfect squares and perfect cubes. So squares, 2 squared is 4, 3 squared is 9, 4 squared 16, 25, 36, 49, 64, 81, 100, 121, 144, etc. And cubes, 2 squared is 8, 3 squared is 27, 4 squared is 64, 5 squared 125, 6 squared 216, 7 squared 343, and 8 squared 512. So double check our first answer, 2 square root 15 over 5. Square root 15, half of 15 is 7.5, so we can only look for numbers less than 7.5 in our list of perfect squares, which would be 4. 15 is not divisible by 4, so we cannot simplify the square root of 15. In the next example, the cube root of 45, half of 45 is 22.5, so we would be looking at numbers smaller than 22.5, which is just 8. 8 does not divide 45, so our cube root of 45 cannot be simplified, which means cube root 45 over 12 is our simplified answer. Now if we have a binomial denominator, if it's a square root in the binomial denominator, we're going to multiply top and bottom by the conjugate of the denominator. The conjugate means the same binomial, but opposite sign. Two over 3 square root 5 minus 4. Step 1 is to reduce. We can't reduce this at all because our numeric coefficients, which are 2, 3, and 4, they don't have a common factor. 2 and 4 can be divided by 2, but 3 can't. It'd have to be all of them if we could reduce. So if it was 2, 6, and 4, we could reduce those 3, but in this case we cannot. Step 2, we want to multiply by our conjugate. We have 2 over 3 root 5 minus 4. We want to multiply top and bottom by the conjugate of the bottom, which is 3 root 5 plus 4. Same binomial, different sign. 3 root 5 plus 4. We multiply the 2 into the brackets. We get 6 root 5 plus 8 over, multiply the binomials together, so first term in the first brackets to each of the term in the second brackets, then second term in the first brackets to each of the terms in the second brackets. 3 square root 5 times 3 square root 5 is 9 square root 5 squared. 3 square root 5 times 4 is plus 12 square root 5. Negative 4 times 3 square root 5, negative 12 square root 5. And then negative 4 times 4 is negative 16. So what we're always going to get when we multiply a binomial by its conjugate, the middle two terms are going to add to 0. And then the other two terms are going to be perfect squares because they are the square of the first term and the square of the last term. So we can get rid of our square root. We have 6 square root 5 plus 8 over 9 times the square root of 5 squared. Square root and square undo each other, so it's 9 times the whole number 5, and then minus 16, which gives us 6 square root 5 plus 8 over 9 times 5 is 45 minus 16, which gives us 6 square root 5 plus 8 over 45 minus 16 is 29. And then we look at our numeric coefficients. We have 6, 8, and 29. Is there a common factor? No, we don't have a common factor there. So that's as simplified as we can get. 6 square root 5 plus 8 over 29. Next one, square root 5 over 3 square root 2 minus 2 square root 3. Step 1, we want to reduce. And again, we can't reduce anything. We have a numeric coefficient of 1, 3, and negative 2. Can't divide those. There's no common factor there. Our radicans are 5, 2, and 3, and there's no common factor there. So no reducing. Step 2, we want to rationalize the denominator, in this case by multiplying by the conjugate because we have a binomial denominator. We have square root 5 over 3 root 2 minus 2 root 3. We want to multiply top and bottom by the conjugate of the bottom, which is 3 root 2 plus 2 root 3. Multiply the root 5 into the brackets. We get 3 times square root of 10. 5 times 2 is 10 plus 2 times the square root of 15 over 3 root 2 times 3 root 2 is 9 root 2 squared. 3 root 2 times 2 root 3 is plus 6 root 6. Negative 2 root 3 times 3 root 2 is negative 6 root 6. And then negative 2 root 3 times 2 root 3 is negative 4 root 3 squared. Again, our middle terms add to 0, and our outside terms are perfect squares. Square root and squared leaves us with the whole number 3. Square root and squared leaves us with the whole number 2. Simplify, we get 3 square root 10 plus 2 square root 15 divided by 9 times 2 minus 4 times 3. We get 3 root 10 plus 2 root 15 over 18 minus 12. 3 root 10 plus 2 root 15 over 6. Looking at our numeric coefficients, we have 3, 2, and 6. There's no common factor there. We can't simplify square root 10, and we can't simplify square root 15. So this would be our final answer. 3 square root 10 plus 2 square root 15 divided by 6. Simplify each quotient. Identify the values of the variable for which the expression is a real number. Starting with our restrictions. In this case, 3 over 2 times the square root of 6 over 27b, we have b under a square root. So we would need to say that b has to be greater than or equal to 0 for the square root. We also have b in the denominator of a fraction, and if b was 0, then our denominator would equal 0. So we need b to not equal to 0 for our denominator. Then we put these two restrictions together. B has to be greater than or equal to 0, but b can't be 0. Then b has to be greater than 0. Let's split up our fraction into two radicals. We have 3 square root 6 over 2 square root 27b. Let's see if we can reduce it all. Our coefficients are 3 and 2. We can't reduce those. Our radicans are 6 and 27b. We can reduce those. 6 and 27 are both divisible by 3. We divide by 3, we get 2 on the top. 27 divided by 3 is 9, so we have 9b in the root on the bottom. 9 is a perfect square. We can evaluate that. We get 3 square root 2 over 2 times 3. Square root of 9 is 3, and then we still have square root b. Then we can reduce. We see we have numeric coefficients on the top of 3, and on the bottom we have 2 times 3, so the 3's divide out, and we get square root 2 over 2 square root b. Are we done? No, we're not done. We know we're not done because we have a root on the bottom of the fraction. We need to make sure we rationalize our denominator. So now we want to multiply top and bottom by the root portion on the bottom, which is root b, and that's because it's a monomial on the bottom rather than a binomial. So we just multiply by the root portion. Then we get root 2b on top over 2 times the square root of b squared. And then square root and square undo each other, so we get square root 2b over 2b with no square root. And then we can't simplify the square root of 2b. We can't reduce any coefficients or radicals, so this is our final answer. Negative 7 over 2 times the cube root of 9p. Starting with restrictions, we have p under a cube root, so there's no restriction for the cube root. We can have negatives under the cube root. No problem there. But we also have p on the bottom of a fraction. If p equals to 0, this whole denominator, 2 cube root 9p, is going to equal 0. So we'd have to say that p cannot equal 0. Let's simplify, starting out with, can we reduce our coefficients, -7 and 2? No, we can't. Can we reduce our radicants? No, because we don't even have a radical on the top. Can we simplify our radical on the bottom? No, we cannot simplify cube root of 9 or cube root of p. Next step, we want to multiply top and bottom by the cube root of 9p 2 times. We need to do it 2 times because it is a cube root. So we're trying to get a cube, which means we need to multiply it 2 times to get a total of 3. On the top, we get -7 times the cube root of 9 squared p squared. On the bottom, we get 2 times the cube root of 9 to the power of 3, p to the power of 3. So the cube root and the cubes would cancel out, and we get -7 cube root of 9 times 9 is 81 p squared over 2 times 9 times p. Can we simplify the cube root of 81? Yes, we can divide 81 by 27, which is a perfect cube. -7 times the cube root of 27 times 3, p squared, over 2 times 9 is 18p on the bottom. We can take the cube root of 27, it's 3, so -7 times 3 cube root of 3p squared over 18p. Then we can simplify our coefficients by dividing out 3. 18 divided by 3 is 6. So we get -7 cube root 3p squared divided by 6p. That is our simplified answer. Last example, 6 over the square root of 4x plus 2. Starting with restrictions, we have 4x under a square root, so 4x has to be greater than or equal to 0, which means x has to be greater than or equal to 0. We also have square root of 4x plus 2 as a denominator, so we need to know when is that going to equal to 0, because that has to be a restriction that it can't equal 0. Well, the square root of 4x will always be a positive number because the square root of a number is always positive. Plus 2 is always going to be greater than 0, so we don't have to worry about the denominator equaling to 0. We just say x is greater than or equal to 0 for the square root restriction. Simplifying, 6 over square root of 4x plus 2. I see that I can simplify my root. It's a 4, square root of 4. I can take that out and we get 6 over square root of 4 is 2 square root x plus 2. And then I see that I can divide my coefficients. I have 6, 2, and 2. I can divide all of those by 2 to reduce our expression to 3 over root x plus 1. Now I need to rationalize the denominator. It's a binomial denominator, so I want to multiply top and bottom by the conjugate of our denominator, root x minus 1, root x minus 1. On the top, I get 3 root x minus 3. On the bottom, root x times root x is root x squared. Root x times -1, negative root x. 1 times root x plus root x. Positive 1 times -1 is -1. Middle terms add to 0. The root term, square root and squared, undo each other. We're left with 3 root x minus 3 over x minus 1. We can't simplify our coefficients because we have 3, 3, 1, and 1, so there's no common factor. So this is our simplified expression. That brings us to the end of Chapter 5, Lesson 3.